But with that, I think we should start the meeting. And so I will call on the first speaker, Professor Pierre Ramond from Florida. He was, as many of us, one of the people at Caltech. He was there in the 1970s. And he will probably tell you more about his relation to Richard Feynman and Caltech. But I just give you one piece that I remember. Because since he's French, Richard Feynman liked to come into his office and give some talks in French. There was fake French, but he had learned it, and it was hilarious. And this is what creates, this nice atmosphere when you have someone that can go outside. We heard that very much at the exhibition, but you go outside the ordinary frames, and that creates feelings, and you really stimulate each other. But I shouldn't say more. So he will now tell you about Feynman and quantum electrodynamics and Feynman's path to Nobel and beyond. So Pierre.
Okay, well, thank you very much. I'm kind of the introductory speaker on this, and I will talk about Feynman in his own words. So I will. What I will do is that I will basically tell you how Feynman got to the Nobel Prize. Secondly, we will have a little interlude whereby when 1978 Feynman was teaching this course on quantum field theory, rather advanced course, and I decided to attend it together with my friend Graham Ross. And we basically was fine. I mean, we heard the great man, etc. We were very, very pleased, but unfortunately he was getting rather ill at that time. And the course, he basically told us in the cafeteria at Caltech called the Greasy that, oh boy, I'm going to be operated tomorrow. We didn't know this. And that was that. And so anyway, I was asked the next year to teach his course. And then in the subsequent years, we talked a great deal because of the overlap. I mean, I wanted to always check with him and etc. because, it was very humbling and very scary because he was the guru in the field, and he was also rather unpredictable. So we were all terrified of him, and at the same time we were thrilled by him. Okay, so this is what, and then so let me go to the next thing. Oh yes, that's it. Good. So unfortunately, for some reason, this is a bit too small, but I don't know exactly what to do about it. So the road to Stockholm, and what I'm going to use is the Feynman's Nobel lecture as we go along. And for those of you who are young and you should never read such a thing. What you should do is concentrate and read Dirac or something like that, textbooks. But nevertheless, it's very important because it tells you his intellectual path through a rather complicated, murky thing. And how he was able to gain some clarity, and eventually, even the Swedes had no choice but to send him to Stockholm. The second one is about his teaching on quantum field theory, and the course he gave in 1978. There had been a great deal of progress in quantum field theory. We have here Professor Callan, whose equation is part of this, and his course was tremendously modern. He was aware of everything that was going on. And so he was not teaching the old quantum field theory, which had been taught for many, many years, but it was always at all the novel things. But I'm not going to bore you with that. What I will give you is a bunch of anecdotes, because Feynman liked to basically say rather provocative things, and some of which are really amusing, and hopefully. And then the third one is Mr. Smith goes to Chapel Hill, and then I will let you, I won't tell you what it is yet. Okay? So here we go. So let me first read this. Unfortunately, well, the young ones in the audience have no problem because, okay, and so that's all right. So at 17, Feynman enters MIT, 1935, and by the time he graduates, he's recognized as one of the most promising physics students ever, okay? But so by his junior year, and I hope you will emulate him, he had read Dirac's Bible, Principle of Quantum Mechanics, and moved on to Dirac's formulation of quantum electrodynamics, which had been formulated basically 10 years or so earlier, 1928. Where there was a serious problem, when you calculated things, you ended up getting, for physical quantity, infinity. And that occupied a great deal of people during that time. And one was associated with something called the self-energy of the electron and also the infinite number of degrees of freedom in the field theory. And nobody really understood how to dissect where they came from, etc., but they were there. And that was a big problem. So Feynman, how should I say? Feynman was very brash, very bright, and he said, oh, I have the solution, okay? There are no fields. They're just electrons in the world, and therefore all these difficulties go away. And this is what he formulated probably as he was a junior or a senior at MIT. And from his point of view, why didn't anyone think of it? End of story. That's it. Okay, that was, okay. And then he said he fell in love with this idea, and what it means is that there's a great deal of passion in him. And that was a completely passionate approach. And it was in his guts. Okay? So, now, his first paper, however, in 1939, when he was a senior, was Forces in Molecules. And I'll read you the abstract because it's a complicated problem, but it kind of tells you already something. The force on a nucleus in an atomic system is shown to be just the classical electrostatic force that would be exerted on this nucleus by other nuclei and by the electron's charge distribution. It simplified all the quantum mechanics and stuff. And that is still was used by chemists a great deal, and this was Feynman's original stuff. In the acknowledgement, John Slater was the head of the MIT group at that point, and he thanks two people. The second one is Conyers Herring, who basically, as I put here, was a solid-state physicist, very distinguished, and got the 1984 Wolf Prize, actually. I mean, so he was talking to the right people, and there was no messing around. In other words, he wasn't, he was kind of there. Now, many years ago, after one of Feynman's pontifications to the undergraduates at Caltech, one of them came to me and said, it's amazing, this Feynman stuff. He does all this stuff and he doesn't know any mathematics. Okay? And Feynman loved to basically get people to believe something about him that wasn't true. Okay, like French, like speaking French. He didn't know French. He didn't fool me. Now, so anyway, so there is the Putnam competition is a mathematical competition for undergraduates, which started in 1938. And in 1939, he was one of the 5 winners. Okay? It's not too bad. And, and for somebody who doesn't know mathematics, it's quite remarkable, in fact. Okay? Okay, all right. So, of course, he was kind of blowing everybody away. And as a result, I mean, and I think it's to Conyers Herring, because Conyers Herring was a Princeton product and had been at Princeton for a while, and apparently, anyway, he enters Princeton graduate school. Okay. All right. Okay, so what I want to do, thus began the journey. Okay. Now, his modus operandi is the following, and this is very important, because I would say, first of all, he likes playing cat and mouse with his ideas. It was a big game for him, okay? He was unbelievably tenacious. When something was in his way, okay, he really tried he didn't give up. And this is, okay? He had, of course, an amazing ability to calculate, and he loved calculations. This was very, very, very big. And he had a reverence for experiment, okay? And then he always wanted to understand complicated things in a simple way. And then, of course, he had the intuition for the right answer, which only the great, great physicists have. And I don't know where that comes from, but it's there. Okay? So the Feynman Nobel lecture, even though what I said to you earlier, okay, is must-reading for aspiring physicists in a sense that he kind of bears out all these qualities as we go along. And that's very important. Okay. Now, first obstacle. So he goes to graduate school, and then he learns that a radiating electron loses energy. The loss is reflected by something called the radiation resistance, he calls it, but it's reaction, etc. And right away, he cannot ignore the self-energy. Now, the self-energy is that it is something that the field emitted by an electron hits back on that electron, but if there's no field, it don't hit back, so to speak. And that was a problem, okay? So, therefore, he cannot ignore the self-energy, and he did not know that because he was just an undergraduate. Brilliant. So he calculates in his version, okay, and he starts basically looking at things. So he calculates, he shakes an electron, it sends a retarded signal to another electron, which receives it, then it sends something back. So there's a time delay that's not at all like radiation resistance. Okay. Furthermore, the radiation resistance he got was in the physical one is independent of mass. This one was not. Okay. Now, Feynman's idea is stupid on many grounds, and his advisor Wheeler admonishes to him little steps for little people. And Feynman, many years later, remembered that because I suspect in the interim, not anybody said that to him. Okay, but this was it. So, all right, but this was Wheeler, and it was Feynman. And, Wheeler starts asking, why can't you shake a source that emits both retarded and advanced signals? By the way, I asked Wheeler at some point about the episode, and he remembered the remark, but then he added, when he remembered having said little steps for little people, but then he said, but the idea of no fields was mine, he said. So we'll see. Anyway, so what happened, he said, Feynman starts calculating, and this is the thing. When he has a challenge, he just calculates, okay? And then until he gets into a contradiction or something wrong, makes him think, and then calculates again, adjusts a little bit, calculates. Okay, then, all right, so this is what he says. Now, of course, people like Dirac, his hero, had calculated the classical thing about the self-energy of an electron in classical physics, found actually that there was an infinity, but they were normalizing its mass. That's a bit too technical, but okay. But Feynman, interestingly enough, he said later that he was in the habit of reading every paper in the physical review. But then I learned that his reading was a little bit different than the way I would read, because he would read the abstract, and then he would reconstruct the paper as a challenge. And so that is remarkable on two grounds. One of them is that he could do it, and the second one is that the physical review was very small, and it was possible to do that. Okay? Now, so let me give you an idea about his simplicity of thought. Consider a source, S, at the center, and there's a wall of absorbers here, left and right, okay? In his thing, he said 10 light years away, okay? And then you shake this guy, okay? And this guy sends an advanced and a retarded signal, okay? And then he has a little test charge here, and I'll let you worry about this later, but okay? The question is that this test charge will receive signals directly from the source S, but also from the guys on the left and right walls who have absorbed the signal and coming back. And what he notices is that the source, so the advanced signal from the left wall hits the test charge at t-1, because as the advanced, remember, it takes 10 seconds to come here, and then etc. And then at the end of the day, the two signals we receive by the test charge at t equals -1, which is when advanced and no causal stuff cancel out if they have the same strength, and the two signals at t equals +1, which is the one you would expect, add up. Okay, and therefore Feynman's dream is that I've solved the problem of the self-energy. I don't have to worry about that. Those guys are the same. Okay, so that was the progression towards an idea. Okay, but notice the teacher's stuff. I mean, the simplicity of the idea. Okay, although Wheeler helped. So electrodynamics is now written in a particular way. This is a bit technical. This is the action for, this is the particle, electron at some position, the interaction with a particular thing called the propagator, okay? And this is what it was. This was Feynman's first propagator. Another one came later, which is famous, is that this is just a delta function of the separation square. So it's conformally invariant, or time symmetric if you want. You can talk it in different ways, okay? And the question, why should these signals be equal? Well, he and Wheeler devised what's known as the absorber hypothesis, which says that the sum of all total radiation from all the electrons is absorbed, okay? And that's it, and that was this. So there was a strange formulation, since the path of a particle at a given time depends on what happened to it previously. In other words, this was very unusual, because in regular quantum mechanics, in ordinary mechanics, as you teach to the students, you have the state of we have the system at a given time, then you have a differential equation, which takes it a little bit later and a bit later. This was something that had to do with this. So already he had developed a view of classical electrodynamics in a very different way. Okay? So in his mind, that's what he was thinking, which of course contemporaries were not thinking about that at all. Contemporaries thinking about equations. Oops, sorry. Okay. So let me see where we are. Okay, so it's a strange thing. Feynman was at ease with it, although he said he was disdainful of the Hamiltonian formalism at that time, But that was Feynman. Feynman could be disdainful of many things because he didn't need to, he just was Feynman. Okay? So, but he kept on playing. So for example, this propagator he changed, he gave a width to the propagator, and so he introduced a little scale. He played all kinds of games, and he calculated. Okay? All right? And then Wheeler, as actually Robert talked about on Saturday, Wheeler thought really that there was only one electron in the world, and that basically think of it as a yarn of for knitting, etc. The world, and the yarn is a world line of the electron, and you cut it anyway, and you have yarns going this way and yarns going that way. The ones going this way are electrons, the one going that way are positrons, and okay. So that was one of Wheeler's idea, but it was stupid because there are many more electrons than positrons, and it didn't really make sense. But nevertheless, it will be used later. Okay, so so these guys were playing. Okay, this is really far away from the experimental stuff. Okay, this was a conceptual business. Okay, but now quantum mechanics cannot be ignored, because by that time, except in France, I think, where the hidden variable theory was lone pilote, was working pretty badly, but nevertheless, okay, so they didn't quite know what to do, and all he had was the position of the electrons and the velocity of the electrons. And the quantum mechanics was quite different, because you had the position and the momentum. And you know that is the difference between two formalism, one due to Lagrange, one due to Hamilton. Okay. However, he was lucky. In September 1941, the German physicist called Herbert Jelle, who was recently released from internment, in France actually, arrives in Princeton, where he meets Feynman over beers at Nassau. Okay? So let me tell you a bit about Jelle. Jelle's father was a general, but Jelle was a Quaker and a pacifist, refused to serve in the German army, and therefore was an undesirable from the point of view of the Nazis. And he went to France, and during the war, at the very beginning of the war between France and Germany, he was interned in a camp in the south called Camp Gurs, which was actually set up for the refugees from the Spanish Civil War a few years earlier. But anyway, he was in there, and mostly they were Jews, German Jews who were interned there. But he was released because Eddington intervened on him. Anyway, it's a long story. He arrives there, and and he started as what I call during physics chit chat. It's just the physicists talk to one another. They don't ask, what kind of beer do you like or something. They mostly talk about some physics stuff. And then Feynman expressed his frustration as being unable to describe quantum mechanics on the interposition velocities. And so Yele points to him a paper by Dirac in an obscure journal, where basically Dirac had set up such a formulation using sum over path, where the classical path was actually singled out as this as h bar went to 0. However, Dirac was not happy with it and not pursued the approach, and because it was based on analogies. But Dirac, was like an oracle. So if you read ancient history, you ask the oracle at Delphi, right? Delphi, and you go and the oracle opens a pigeon and says, well, this is the way it is. And Dirac was a bit like that. Nobody knew where it came from, but it came. Okay, this was the thing. So he had this, there was this feeling about him. Okay, so, all right. So Feynman said, oh my goodness, this is exactly what I was looking for. The next day, they go to the library at Princeton. By the way, this was a time when libraries were closed. See, nowadays libraries don't exist. But so, but what happened is that there are many things in physics where people have to wait. For example, Dirac had to wait a whole weekend to go to the library when he etc. But they were closed. Now you've got the internet, and it's quite different. Okay, so. And they find a paper, and then days later, Yele asked Feynman about the paper, and he got what is a Feynman-esque answer. And this is Feynman talking to me, because as I was teaching this course, I wanted to know his feeling on these things. He said, not only did I read it, said Feynman, I derived Schrödinger's equation from it. Kind of nonchalant answer. And years later, Feynman remembered Yele's eyes seemingly bulging out like saucers. And what Feynman had done is use this Farragut's expression, damn the torpedo, and calculate and see what happens. And that was that simple, okay? But of course, he could do it. Yele apparently had tried and could not do it. So he was, and Feynman had turned Dirac's analogy into reality. There is, in fact, in a book published by Michel, there is one of the congratulatory telegrams after Feynman got the Nobel Prize. Yele sent, and then Feynman says, Dear Dr. Yele, it's all because you showed me Dirac's article on the library at Princeton. Thank you very much. Okay, all right. Okay, now, so Dirac writes his thesis, 1942. It's called The Principle of Least Action in Quantum Mechanics. This is a very bizarre thesis because, excuse me. No, that was the wrong thing. See, we're going backwards in time. Okay, all right. And it is called The Principle of Least Action in Quantum Mechanics. He uses the sum over path. It's purely non-relativistic, okay? And, there's no reference to Dirac. There's plenty of reference to Dirac's principle of the Bible, okay? And there's no reference to Yele either, although later on and then what happened is that he had basically made some applications in terms of forced, harmonic linear oscillators, which turned out to be too simple and kind of obscured the problem. And, and then he tried to apply the Feynman. He was thinking, he didn't apply in his thesis, but he was thinking about applying the Feynman-Wheeler. But then there was no time to go any further, although he said, I got a kind of funny feeling that things were not exactly right. Okay, but he became otherwise occupied. Okay, well, so December 41, the United States enters the war. Okay, and Bob Wilson gets Feynman to join the Manhattan Project using diffusion of isotopes at first, but anyway, and soon during the war work, so. He's thinking about during the war, he meets Hans Bethe, who was the chief of the theory division, and so apparently he and Hans Bethe got along very, very well, and et cetera, and of course Dirac made his mark right away. This is too small. I was looking for Michael Kreutz's father on the T division, but was he on the T division?
No, he was experimental.
Yeah, that's exactly. So I couldn't find his name. Good. But if you look at this, and if we could blow it up, you have here the who's who of theoretical physics in the United States. Okay? I mean, so you see Feynman heads a division. He's also a consultant on the computing, but Feynman, the consultant, meant he was it. And there's everybody there. I mean, whatever name you have, I mean, except you can't read them, but it's all right. Okay? All right? But it's okay. So of course he was fantastic. And I mean, unfortunately, but you can look at it on a microscope. And so in his Nobel lecture, he hardly mentions the war years. He said there was the war, except he says he was still thinking about it. He said he had long bus rides because people in those days seldom flew. Okay, and he was able to do some calculations, etc. And then he kind of narrowed down that actually a lot of his thesis was not quite right. But it did not matter. Okay. What happened is that they were complex, and when you compute energy, they were complex, etc. It was not unitary. It basically did not work. Okay, and but nevertheless, for you young ones, see, he basically had developed a set of very important ideas, and those ideas, even though they were not bearing fruits, a bit like, well, it's not like string theory, but it could be viewed as like string theory, that it has not really been applied to the real world, but it's something you keep on your head and your mind, because some of the techniques actually may become. Okay, I say that. Anyway, okay. So the war is over. Hans Bethe, of course, recruits him to Cornell, right? I mean, no problem at all. And it's time to take stock from Feynman's point of view. Rather depressed, but then after the war, whoever was not depressed, I mean, he had been, part of the team that, an important part actually in getting the atomic bomb to work. And the reality of the atomic bomb struck a lot of people. And I said, my God, there was the physicist attitude, I can work, I can do it, And then the reality of it is extremely sad. And okay? All right. But he was totally familiar with a new way of doing quantum mechanics by relating quantum mechanical amplitudes to path. Okay? All right. Now, interestingly enough, he kept on working. Like, for example, one thing that bothered him was the Dirac equation, which has no classical analog. So he was trying to understand, how can I understand the Dirac equation in terms of path? And he found that he could do it in 2 dimensions. Another thing about Mr. Feynman, because Mr. Feynman didn't bother him to change the number of dimensions. He made it work. He saw that it worked. And so there were 2 components. One component was path moving left, and the other was path moving right. Okay, but he could never go up to 4. But he was playing. Okay, all right. As I said, okay, there he is. Restless Feynman keeps playing, inventing little models, calculating. Okay, just pushing. Okay. Now, I don't know how his children felt about him, because he probably, from their point of view, he wasn't doing anything. But, that's what theoretical physicists like. Okay, so, but now comes an incredibly important event, okay? Is that these ideas about quantum field theory and everything, suddenly there's an experimental number that comes out. There's the Lamb shift, okay? And that is a finite number. It's about 1,000 megahertz, etc., and there is it's an experiment. So Feynman, of course, gets very excited, like many people in his generation, because that's kind of a target. This is something everybody wants to calculate, that number. Okay? But Feynman is very lucky in a sense, because he's in the same place as Hans Bethe. There was a famous conference called the Shelter Island Conference, when people talk about such things, I think. But anyway, as I said, Feynman's psyche lies an irresistible urge to explain that number. There is no, because it is a target, okay? And he keeps on going, right? Okay, so Bethe thinks that the self-energy of the infinity of the electron self-energy will cancel out when you do it right. But he had used a non-relativist approximation. There was still an infinity left. It was messy. So Feynman and Hans Bethe started calculating, but it wasn't working. They made all kinds of mistakes. But then suddenly, Hans Bethe actually had estimated it, and Feynman calls Bethe's physics feat of arms the most important discovery in the history of quantum electrodynamics. So I think it's correct. Okay, So, but they're full of ambiguities because they were infinities, and you had to you had to do a calculation, and you were not using the rules because you had infinities, and you say, well, I can neglect this one, I can neglect that one, and this one looks like this. And it's exactly the kind of things Feynman Dirac could never do in his life, for example. But this is what those guys were doing. Okay? All right. Okie doke. And now, all right, so Feynman says himself, now he has to learn to make a calculation, which is a very interesting statement because that's all he was calculating, but nevertheless. Okay? So, of course, the result, okay? So he starts from scratch, using Dirac's electrodynamics with a retarded, highly peaked propagator of width A, okay, and he calculates, okay, gets a tutorial from Bethe, calculates the lamp shift, finds that the logarithm, infinite logarithm here cancels out, okay. Now, what happens, he had to make a lot of guesses on the way, okay, all right. The first guess is the relativistic rules of interaction, but he kind of knew that from the path integral method. He kind of knew how the vertices, in a sense, are relatively easy, okay, once you know the Dirac equation, okay? But the most confusing stuff in his mind was how do you go to the relativistic case, okay? But then he remembers Wheeler's old idea. And Wheeler's old idea said, well, look, if I have a charge Q here, and I have a charge Q minus 1 here, how can I do it? Okay, well, you can basically add here an electron, or you can take away a positron from this guy. That's it. That was that simple, okay? Now, imagine that we are talking about a system where the equations are complicated, everything is complicated, but there's this little kind of haiku. It's sort of like a physics haiku. Just a few little things like that, okay? All right, okay, and that gives rise, of course, to the new propagator, which does this automatically, and as Feynman said later on, he says they call it delta sub f. I don't know why, but anyway, that was, of course, his thing. Okay, and what surprised the heck out of him was that in his calculation, the Coulomb and the radiation parts were basically linked together by symmetry. Okay. Furthermore, you were automatically summing over all possible polarization. None of this, whereas the whole generation was at the time was looking at the Hamiltonian part, the Coulomb part, and the radiation part, and Feynman could do it just like that. And why could he do it that way? Because he had developed everything in a manifestly relativistic fashion. Okay? All right, this is kind of, but then of course he has done it because he was Feynman. Now, this is something, I will interject this one. So to organize the calculation, he invents his famous graphical rules that everybody talked about. We heard a lot about it, okay? And Feynman used to say it's just perturbation theory plus logistic, and that's the hard part. Now, one of Feynman's favorite textbook of the time was a statistical mechanics book by Meyer and Meyer. The second Meyer, or the first Meyer, depending how you look, is Maria Goeppert Meyer, a Nobel laureate. And what they developed was a graphical method to evaluate the partition function. Okay? And it's called the cluster expansion. So you look at cluster of molecules. And so, for example, the function, you have a two-body potential between particles I and particle J, okay? And if you do it this way, this falls off relatively fast. So you can have clusters of 3 molecules, either like this or like that, and you see the diagrams are different, and they are, with the rules that they have, the contribution from these diagrams will be different. Then there are irreducible clusters. You can see how this is one particle reducible, for example, et cetera, okay? And these rules are there, and I suspect that the idea of a graphical expansion, okay, which he had read in his thing, was actually, he adapted, etc. But the idea of that probably originated in that book. This kind of, all right. Now, Feynman, I asked him about these diagrams, and he said that, I don't know if it's true, but he said that on a Sunday morning in Ithaca, he remembered that he was playing with these diagrams on the floor in his pajamas, he said, and he was drawing diagrams after diagram, like a kid, with a Lego thing, and he was wondering whether this would be of any use. I'm not sure this part of the legend, right? Okay. All right, now, So I want to say one thing before I finish this part. It's most striking that most of the ideas developed in the course, these are his words, of this research were not ultimately used in the final result. Okay? The half-advanced, half-retarded potential was not finally used. The time-symmetric action expression, which is that propagator, was not used. The idea that charges do not act on themselves was abandoned. The path integral formulation was useful in guessing the vertices, but it was not really absolutely necessary. And finally, the idea of positrons moving backwards in time was strictly speaking not necessary, because you could have used the negative energy sea of Dirac just as well. It would have been a big mess. Okay? So, and he ends his Nobel lecture on a very personal note, okay? Which is, so I was happy to hear on Saturday the, oops, sorry. Oh no, okay, hold on. Yes, I was happy to hear on Saturday some mention of Nobel's analogy, Feynman's analogy from no less than the Minister of Finance, who happens to be the head of the Research Foundation, so it's good. So he said, so what happened to the old theory that I fell in love with as a youth? Well, I would say it's become an old lady. And the young today will not have their hearts pound anymore when they look at her. But we can say the best we can for any old woman, to say that she has been a very good mother and she has given birth to some very good children. Okay? Anyway, it's okay. Now, I'm going to the next thing. I'm going to go fast now because, okay? So, I attended this course, okay? And there are all kinds of subjects that were, okay, that were mentioned. And for those of you who basically would look at any modern textbook on the field, that would not be very different, okay? So there are a bunch of sayings. Physically, there's nothing divergent provided you ask the right question. What to do with divergent integrals? In general, they're infinite. That was very deep. And his quantum theory of any field is just the question of computing the amplitude and finding a given shape. That's very important because he had a visual. He always had a visual. Actually, you're talking about visual a few days ago. There were the equations, but there was always, I think he probably could close his eyes and see these things, okay? All right? And then the question of quark confinement, which is still not solved, and he has this marvelous saying, oh no, okay, yeah. All we know about confinement is the collapse of a proof that it does not confine. That's still true today. Okay. And he even talked about hidden variables, and I think I will not talk about it. So, okay. And then he continues with a bunch of saying before I go to the last topic. Okay? So we are better than mathematicians. We only say 1 to infinity. Okay? It's necessary that the students be better than the professor in something, otherwise we're making no progress for the race. Okay? If it's dark, it should be dark when you're running. Yeah. Throw away the self-energy of the electron in a relativistic way. That is what took 20 years. It's a goddamn harmonic oscillator because he had been betrayed by the goddamn harmonic oscillator. Okay? All right. And now I want to give his two things about quark masses and mixing, which is something I happen to be working on. And he said, it's injected in a theory by hypodermic needle. And he said, you want more than a Nobel Prize? You want to become a king? Figure that out. Okay? And after that, he said nothing about it. Okay. So now I go to my third thing. So beyond Sweden, Mr. Smith goes to Chapel Hill. So, in January 1957, Bryce DeWitt and Cécile DeWitt-Moret organized the inaugural conference of the Institute of Field Physics created by industrialist Bonson at the University of North Carolina with Bryce DeWitt as the head professor. It's called and the conference is called The Role of Gravitation in Physics, and it was an attempt to kind of have kind of understand where we are in gravitational physics. Okay, and it turns out it played a very important role. By the way, this should be a hint to people who have money to give to conferences, because it was not clear to many people that such a conference would be useful because these topics had been around, etc. But this was the right time, and it's one of these workshops that people still talk about today. Okay? All right, so what happened is this. And I want to talk to you just about Feynman's role in it. Okay? It's called, skeptical Feynman registered as Smith. He didn't register with his name. Okay? Like you know, you don't want to be known, so this is what you do. And yet he had said, the problem of the relation of gravitation to the rest of physics is one of the outstanding theoretical problems of our time. He was very focused on that, but he did not like what people were doing. And I will, okay? So the first question was, does gravity need to be quantized? Believe it or not, people were worried about that. So Feynman makes a Gedanken experiment. So this is a Stern-Gerlach setup, and he has a little macroscopic little ball here. He puts rods, okay? And in that case, it's like a Schrödinger cat, except now it's a Schrödinger ball. I mean, it's a Feynman ball, and moves up and down depending on the spin. That is a macroscopic, okay? All right, and from Feynman's point of view, you have complex amplitude. You have a complex amplitude for the ball up and the ball down, but there's no measurement yet. Okay, this is just a possibility, and they're complex, so they could interfere, etc., etc. That's fine. Okay, all right, and that's a purely reversible thing. Okay. Now let's see. So what does he do? He adds a second ball. He said, well, okay, as a result of this, the gravitational field that this ball has, okay, is going to depend whether the ball goes up or goes down. And if we amplify this gravitational field, a second ball put a little bit there will also go up and down, okay? But from the point of view of an experimentalist, I'd say you could ask yourself, well, forget about what's in between. Just look at what happened at the ball. There, it goes up and down, and those are the two possibilities, amplitude for one, amplitude for the other. Okay? So basically what you have, he added a link, a gravitational link between one thing and the other. Okay? And then he says, I cannot conceive that this link will not be, it has to be basically quantum mechanical, because the notion of amplitudes, the notion of interference should still be there at the end of the day. Okay? And therefore, he believes that there should be that gravitation should be quantized. And this was his way of looking at this, okay, which is kind of, so this is one contribution to the conference. Okay? And there is a great deal of stuff about measurement, which I won't go into, but the fact is that, there were all kinds of objections about this, but he met them, etc. And people usually talk about Feynman not talking very much about measurement, etc. But he was right in the midst of it there. Okay? So, all right. But from his point of view, all it was is that you have an amplitude for the thing to be up, an amplitude for the thing to go down. And if quantum mechanics is, if it is quantum mechanics, then basically they're complex, and they can go on and interfere and do their thing. And he said otherwise, he said we would have some new principle if it's not, And the new principle is that a piece of equipment able to amplify by such and such a factor necessarily must be out of reach of nature, and thus irreversible, because this stuff, okay? And he dismisses this. There's no evidence in quantum mechanics whatsoever for such a thing. Okay, so that is one aspect of it. Okay, now I go back. All right, so let me give you Feynman's view right now of gravitational research. Okay, it's not finished. So he understands, he says there are 5 different things here. First of all, you need to understand classical relativistic gravity without the complication of other things. I didn't quite understand complication, the other thing, probably the rest of physics, but that's what I'm not sure. The general theory of cosmology, okay? We may be able to work out the shape of the world, sorry. You should study the theory to see if anything new is in it which is not contained at first sight. In other words, you calculate and you look for weird thing. Okay? All right. Learn from the philosophy of gravity something of use to other fields, and he says curiosity. So this is his way. It has to be done. Okay? Now, two ways to deal with problems where no experiments. He said the real problem is that there are no experiments available. So what do we do? He said, one, we apply mathematical rigor. Okay, and he said, don't be so rigorous or you will not succeed. I mean, he completely dismisses that, okay? Or else play games. Start calculating things. Start seeing how it goes until you get into a contradiction, okay? So he says, okay, since we're not pushed by experiments, we must be pushed by imagination, which is kind of true, okay? And the real challenge is not to find an elegant formalism, but to solve a series of problems whose result could be checked, okay? Right? So on the one hand, in that case, he had gravity, a beautiful theory. Einstein, you know, it's almost like a holy grail, right? It's Einstein's equations. You don't touch it. It's beautiful. And everybody agreed it was beautiful, okay? But right now, not challenged by experiment. And the rest of physics, which is nuclear physics, beta decay, electrodynamics, okay? You know, awash with experiments, but the overall thing is not yet a beautiful theory, which now we have. That has changed. Okay, so there we are. So he said, suppose Einstein, this is Feynman, you know, suppose Einstein never existed, what would I do? Okay, I mean, you know, well, he says, I would probably start, because there is the Newton potential, right? I would start with a massless field. And then I would play with it, and soon I will find out that it probably should be spin 2, because it's only the force is only attractive, etc., etc. It's very different from, okay, even spin, etc. At that stage, it could be spin 4, but I mean, it's a different story, but he takes the simplest thing, okay? And then he said, well, you know, if we do this, we would have a stress energy momentum tensor which couples with this, okay? So use the classical thing. We would have an equation of motion, okay? And then the next problem in electrodynamics, current conservation is an identity from the field equations, but not here. Okay, that's the first big difference. Okay, so we need to add something more, because it's not as beautiful. So he looks for a cubic term, he puts that in the action, okay? All right, and he sees the beginning of an expansion. At that time, you ask a mathematician, he says, okay? Because you're getting lost and it's getting a bit too complicated, okay? And then the geometric thing emerges from this formalism. So this is 1957, January 1957. His famous lectures on gravitation were published. He gave a course, were only published in the early 60s, but he was already thinking about this in a well-developed fashion, okay? But that's also, you see, what happened is that, okay, this is like Gavroche in a literary sense, namely thumbing his nose at the established stuff and say, what if I do it in another way? And he went into this unknown, okay? And that's, okay, now, all right. Now, he said, maybe we should also use old physics. So he said, well, neutrinos are massless, he said. Therefore, we should use that as exchange of neutrinos. But they don't give rise to the 1 over r square law. Okay? Or you could do it with 3 or 4, but then you have to involve the sources. It gets to be a real mess. In other words, it's terrible. Okay? All right. Now, my last thing. Okay, I don't know how much time I have. Huh? Plenty? Oh, plenty. Oh, good. All right. Okay. Now, so, all right. Okay. So there he is, but he's not finished in his contribution to the conference. Okay? And this is where, and I thought this is a rather interesting topic. Gravitational radiation. Now, gravitational radiation had been, basically, there were solutions. There are famous papers of Einstein and Rosen on the thing, but it was very unclear. Nobody could understand, believe it or not, at that time, because there were infinities in the solutions. And nowadays, of course, the notion of there are infinities, and there are infinities, and there are infinities which have to do because you're in a wrong coordinate system, and there are infinities which are infinities because they are there. I mean, this is basically how it goes. Okay? And so people were still confused, and even Einstein was confused. They were going back and forth as to the reality of this solution. Okay, let me see. Okay. Yeah, this is getting to be bad. Okay, all right. So there they are. Now, so in fact, Einstein was dead by then, but his collaborators thought that perhaps they carried no energy, nothing at all. However, there's a man called Felix Pirani, who was a postdoc with Bondi, okay, showed that actually you can look at the solution and rewrite it in terms of Riemann tensor, gauge invariant stuff. And therefore, he found out that, that this was quite possible. He had written a paper just before the conference, and he presented parts of it there. Okay, that basically, don't worry, there are no infinities. He was in a particular coordinate system. He used a tetrad formalism, for those of you, all kinds of stuff, but nevertheless, there it is. Okay, and then he says, well, all right, he gives a formal presentation, measurement of classical gravitational fields. That is the thing. Okay, so the reality of gravitational field is there. It's first time. Okay, so he said, first of all, in gravity, if you measure, you need more than one particle because you have to look at, because you have the equivalence principle. If you look only at one particle, you go in a frame where the guy is there. But so if you look at two particles, it's kind of different. Okay, so you have to look at that, and you say, okay, measuring the relative acceleration of neighboring free particles yield information about the Riemann tensor. And there's an equation which has been derived by Shield and Singer, I think. And this eta is the geodesic deviation. It's like the distance between these two things, okay? And there it is. And he said one can very easily imagine an experiment for measuring the physical components of the Riemann tensor. That's what Pirani said. Okay, first time ever. So the people who were at this conference, by the way, it was the who's who. Even Witten was there. His father. Okay. All right. But, I think that actually Wheeler probably twisted Feynman's arm to attend. Okay, because but nevertheless he attended. Okay, so this was it. And now enter Feynman. Okay, so Feynman's attitude was that if it transports energy, we should be able to detect it. Why not? Okay, very simple statement, right? And then, so he proposes something that became known as the sticky beads experiments. So you have some bead with a rod connected to it, and then you can take another one which is free to move on the rod. Okay, a gravitational wave passes through. Okay, all right. And what happens as it passes through, this guy starts jiggling, okay? And then this guy here loses heat to the rod by friction as it moves. Therefore, heat is energy. You measure it, and voila, that's it. Okay? All right. And then he goes. He said, well, the gravitational wave, there's a discontinuity in the Riemann tensor on the wave front as it goes along. Okay? And that's what you do. And this is the experiment he proposes. And the next question that he has, of course, but should we be able to generate gravitational waves? Because one thing is that, yes, it could be detected. What can we generate? Which is very strange today because we are in the days of gravitational waves. But there it is. So he proposes a way to do it. And this is how I will end my talk. So he says, well, they can be generated. He said, why not? Okay, that's first thing. And he says, well, if you have put particles and the wave goes through, remember the gravitational field has two transverse directions, and so there's a quadrupole effectively coming, unlike the one. Well, okay. So what happens is that my instinct, he says, because I think it's kind of nice to say, my instinct is that a device which could draw energy out of a wave acting on it must, if driven in a corresponding motion, be able to create waves in a thing. And he says, okay, and the reason is because if energy is absorbed, the wave must be getting weaker. And how does it get weaker? It's because the guy who absorbed the stuff, okay, itself emits the same thing, which goes opposite to it, because otherwise you get a nonlinear system, everything would blow up, okay? And this is how it goes. So he has this very, very simple way of looking at things, whereas the way I've looked at, I would have looked at a lot of indices. Okay, but he never looked at it. He did, but he was always writing this in a nice way. Okay, so he says at this conference, these waves can be generated and are in every respect real. Okay, and at that time, And so so Barry Barish actually was talking about this to me at some point, because I did not know about this meeting, and basically this is viewed by people in the field as the important meeting where the reality of gravitational radiation was finally established. And your father basically contributed in different ways, okay? And right away, I mean, he had always he was always proposing various things like that. So he attended a conference to which he was probably not really too keen to be at, and yet he contributed in many different ways. One, making people think about measurement. Okay. The second one, this, and also talking about setting up the theory of the massless spin-2 particle, basically. Okay, and that was the way it was. So I will end by a few comments. I mean, I've given you a glimpse of the direction in which this person was going. I mean, I was, you know, one of the things that is normal, that is really nice about being a theoretical physicist, is that you get to meet people who are theoretical physicists, because that's what we do. Okay, but the thing among those, there are people who are totally extraordinary, and you can count them in a number of you, less than a number, half a quarter of a, okay, and Feynman was one of them. There were so many dimensions. It's like you had a red light, okay, and you're revving your car, and you have a Ferrari next to you, and you're driving a Mazda, okay? So you make an equal number of noise, but then the Ferrari goes like this, and you say, oh, I didn't know they had changed the light. Anyway, so Feynman was a bit that way. You could talk to him at some level, okay? When he was challenged, he could accelerate very fast. Okay, he could focus immediately, okay? And he was aware of most everything. And that is the way he was. So I never had the pleasure, unlike Rick Field, of working with him. I talked to him a lot, but it was just, it's an exhilarating experience, you know, it's just fantastic. And this is one of the perks of this field. Yeah, you get to talk to people like that. And so I think that there's not only the person who can do, you know, he had an aura about him, and the aura was both his personality, but also the kind of ideas he was throwing at you all the time, at himself actually, and he never gave up calculating, never gave up of looking at things. So that's a lesson. And for those of you who are much younger, even for those of you who are older, you should basically never lose sight of the fact that what you're doing in this is you're just playing. It's a game. It's a game with consequences, but it's a very nice game. And if you can contribute in any way to this, it's totally exhilarating. And it was basically an exhilarating part of my life to be, you know, a few offices away from him. Thank you.